Thank you so much for having me here today. Super appreciate it. I'm excited to share a little bit about the future of interoperability in the Superchain. So my name is Mark, and I am part of the Optimism Collective. So first, let's start off with just talking about what the Superchain is. So the Superchain, in really simple terms, the Superchain is optimism governed block space. 3 words, very simple, but there's more. So it's also a horizontally scalable cluster of chains with shared security. It is also a mechanism to turn zero-sum games into positive-sum games. This is really important. This is like one of my favorite parts about working in crypto is that you get to build mechanism design into your products. It's also infrastructure for the institutions of the future, and it's the substrate to align AI. It's very important that if we have AGI, it is financially aligned with us. So, I'm just going to give a quick little overview about the history of trying to scale Ethereum. So the problem statement, right? It's impossible to scale to global demand with a single computer using today's technology. The Solana people might disagree with this, but I definitely think that we're not going to be able to fit literally everything on a single computer. There's a lot of technical challenges, right? We can see the way the market evolved today. We all have personal computers, we have our phones, right? You don't want to have to literally outsource all of your work and worry about other people, using resources on that computer, competing for them. There's also a lot of social challenges around coordinating a roadmap. If different people have different preferences, they might want to work on different features. So if there's one computer, how do you coordinate what the roadmap is? So the solution, the rollup-centric roadmap. Cool. So high-level overview of the rollup-centric roadmap, right? The idea is to leverage L1 for consensus and availability. And then you can use this marketplace of L2s that are all competing and cooperating with each other to scale execution and product and go to market. But this results in a problem. All the users are fragmented between many chains. And all the users get upset when an application deploys on one chain instead of another chain. It's this zero-sum game, right? Unless the pie is growing really fast and users are coming into all ecosystems, there's this zero-sum game where the same set of users kind of are shuffling between the chains and everyone is kind of competing for this small pie. So what's the solution? It's interoperability between chains. So at a high level, there's 2 ways to think about interoperability. There's application layer interop and there's native interop. So app layer interop isn't built into the consensus of the individual chains, right? There's some assumptions about finality, and when you start building token bridging, there can be fungibility problems and liquidity problems. There's also been many bridge hacks. Those are not great. Now, native interop is when you build it into the consensus of the rollup itself. So what does this mean? This means that the fork choice rule and the proof system for the rollup enforce the interop rules. The big value prop of this is that it makes it much easier to build fungibility into assets, right? Because one of the major use cases of blockchains is, being able to send tokens around. So now I'm going to talk a little bit about how we're thinking about interoperability in the OP stack. So I have this little chart here, a bunch of definitions. If you're interested and want to learn more, you can go to our website up here, specs.optimism.io. You can search for interop and you can see. So basically, at a high level, there's this idea of a cross-chain message. And it's made up of two transactions. There's this initiating message on the source chain and an executing message on the destination chain. So it's two transactions. You first send a transaction to chain A, and then you kind of take the results of that transaction and send it over to chain B. So I mentioned an initiating message. What is an initiating message? It's any log, right? Any log that is produced by a chain in the dependency set. So what this means is you can basically consume a log from a remote chain. All the applications today deployed on Ethereum, they already use logs. We designed it this way to not introduce new mental models around how to do cross-chain messaging. All the applications that have already been deployed instantly start producing data that can be consumed on other chains. So, how do we reliably make sure that a log can make it from one chain to another chain? There's this idea of an identifier. So the identifier is just the set of information required to uniquely identify a log. You really need three pieces of information for this. You need a chain ID to know which chain the log came from. You need a block number to know which block the log is in. And then you also need a log index. And with those three pieces of information, you can point to any log that is emitted from any chain. So now we have this idea of an executing message. This executing message is an event. It's a log. And basically, an executing message contains an identifier and a hash of the log that the identifier points to. So using this construct, we can say the canonical chain only includes executing messages where the identifier and initiating message pair match. So this gives us a nice little invariant, right? All executing messages must be valid. And there's a little pseudocode here on how you would do that validation. But the idea is that if there is an invalid executing message, it gets reorged out of the chain. So we add this special event to the consensus, this executing message event that includes the identifier, which is like the pointer to the log, and a hash of the log itself. And the rollup node checks all of these events and makes sure that they're consistent. And if they are all not consistent, if there's one that is, not consistent, it gets reorged out. And all of these executing messages are validated in the proof. So I mentioned this idea of a dependency set. This dependency set is the set of interoperable chains. It is the cluster. And a chain operator can say, these are the chains that I allow inbound messages from. Without this, there would be no upper bound on the resource usage of the network. This guarantees that you can always check the executing message invariant, that the identifier and the hash of the log match. In the future, we'd like to use a zero-knowledge proof system to remove this dependency set and try to arbitrarily horizontally scale. A cool feature about this is that the host chain that emits the event is also part of the dependency set, as well as L1 can be part of the dependency set in the future. And I think having L1 being able to ingest L1 logs is a very powerful primitive. So I mentioned before, there's this idea of shared security. So all of the chains within the same cluster, they will all share security. They will use the same proof system, and they will also share finality. One thing that I just want to call out, there's kind of two types of finality. There's the finality of the inputs to the blockchain, and there's finality of the outputs of the blockchain. Under this mental model, the idea of an optimistic rollup and a ZK rollup goes away, and it's just a rollup. I think that this is a much better mental model for thinking about rollups, because the optimistic or the ZK, these are descriptions of the bridge and not the rollup, right? This creates a nice abstraction where you can very easily just slot in whatever proof system works better for your use case. So I mentioned fungible assets before. The idea here is that fungible assets become so much easier when you have shared security. Ether is going to be able to be sent between the chains seamlessly, and also ERC7802 tokens. So what is an ERC7802 token? It's basically a mint and burn interface on top of an ERC20. It was created to be kind of ecosystem agnostic. It's compatible with pretty much any cross-chain token type through an adapter, like XERC20. L2 native tokens can just start using it right out of the box. And all the assets that have been deposited from L1, there's a clean upgrade path to upgrading to 7802. So to get shared security, we really need this idea of a shared lockbox. So this is a single contract on L1 where all of the ether is held. And this is to guarantee this withdrawal liquidity invariant, where if you're withdrawing from an L2, you should always be able to get your funds in L1 no matter which chain you're withdrawing from. And this helps to improve the fungibility properties of the ether across the cluster. So now I'm going to talk a little bit about the layers of abstraction that we have. So at the lowest level, we have this smart contract. It's called the cross L2 inbox. This is useful for reading arbitrary logs. You should think about this like multicast UDP. The idea here is that when you create when you create a log, it's not like a forced inclusion, right? It's just a log is created, and you can consume that log at any time on another chain. So it's like multicast UDP. Then we have this higher level abstraction, the L2 to L2 cross-domain messenger, and this gives you cross-chain calls. So this is a higher level abstraction that you can think of like unicast UDP. You say, this particular chain, I want to make this call. And it gives you a property of like domain binding, right? That means that you can only call one particular chain. And you also get replay protection. So this is a really useful abstraction for the Superchain ERC20. So this is basically a token standard that is built on ERC7802 that just natively works and is natively fungible within the OP stack clusters. So now I'm going to talk a little bit about application design. So Interop, I think, kind of creates a new paradigm for how we can think about building applications. So today, many applications are built for a single chain, and when you want to deploy your application to another chain, you literally just copy and paste the code and you just deploy it to another chain. So this results in liquidity fragmentation, and you also inherit the scalability problems of each individual chain. There's no way to balance your usage between many chains. Your users kind of pick whatever chain they want to use, and if there's a lot of demand for that chain right now, then they're going to hit that, the scalability problems and pay high fees. So this results in the application depending a lot on the chains for user experience, instead of the application being able to own its user experience and guarantee high quality at all times. So why is this the case? It's really just the fact that we're really early, right? And the scaling technology is very immature, and we don't have smart contract wallets yet. So I think that we need to learn from Web 2. We need to start thinking about chains as microservices in a wider system architecture. So we need to stop building blockchain apps, and we need to start building applications that use blockchain. So from the point of view of a smart contract developer, you can start thinking about chains as like threads for your application. If we want to design something in an interop first way, one way to think about this is to identify subsystems of your smart contracts that do one thing really well, and then think about how you can kind of shard that and make it into a horizontally scalable subsystem, right? This is really good for applying to bottlenecks. So if you can find your bottlenecks and figure out how to shard that between many chains, then you will be able to get way more throughput. So this, the goal is to get to a world where we can auto scale chains with usage. And every single time a new chain is added to the cluster, your application automatically gets more throughput. So let's look at an example with DeFi. You could imagine that there's a horizontally scalable on-chain order book where the orders are deterministically placed across many chains. Right now, order books generally aren't deployed to blockchains because they're much more expensive than, say, like an AMM. So I think that thinking about an order book in the world of interop could be a really interesting application space to design or to explore. Another example, building an NFT marketplace. So in an NFT marketplace, you can kind of break down two subsystems that are independent. You can look at the minting engine and a matching engine. So in the minting engine, you could imagine just users are constantly minting. They're minting super fast all the time, and it's just specifically handling the minting of assets. And then you could imagine another horizontally scalable subsystem that is doing matching. So it's the trading of the assets. And under this, with this design, I think it's possible to scale far more than, say, deploying it all to a single chain. So this auto-scaling future, very far away realistically. We need a lot of primitives to make it a reality, right? We need smart contract wallets. Smart contract wallets will allow users to, just specify their intent and allow it to execute across any chain. This gives like a load balancing sort of property. We also need some sort of idea of distributed storage. So what would a Solidity library look like that allows the developer to arbitrarily read and write to storage across many chains? We've been prototyping a promise library for Solidity. It might sound crazy, but promises are a nice abstraction. Developers are used to them. But I think that we're going to need a lot of developer tooling that is familiar and provides simple abstractions for native interop first applications to take off. We also need some sort of multi-chain RPC. So the idea here is that we want to kill network switching. it's really annoying when you have to go into your wallet and switch the RPC provider to a different chain. The idea is that to have one cohesive experience and make the cluster feel like one chain, we need a single RPC backend that aggregates many different RPCs behind the hood. And ideally, it's backwards compatible with existing RPC providers. So somebody that's using MetaMask, it can just work. So now I'll tell you a little bit about how to contribute. So we have open specs. You can scan this QR code. It'll take you to specs.optimism.io. I think specs are really important. They help us find bugs. They help us, know what we're doing. They help us grow our ability to coordinate with more people. So all of our specs are open. Please check them out. Give comments if you would like. We're also building free software. I think that this is very, very important. I think that it's a fundamental human right that anyone can, create their own rollup, deploy it, transact on it. So it's very important that the OP stack is, it's MIT licensed. Geth is GPL. So it's all free software. Feel free to fork it, play with it, do whatever you want. We're also building out some public DevNets for Interop. So at Edgelana, we launched a DevNet. It was a lot of fun. We deployed some applications to it. We built a relayer, and we were sending cross-chain transactions. We're going to continue improving our DevNets, and you can follow along right here in our docs. This will contain all the information on how you connect. Cool, thank you.
Any questions?
Here.
Can you elaborate a little bit more on the horizontally scalable subsystems? Are you thinking that effectively, devs write one application that will dynamically spawn different chains to, be able to serve more demand and also dynamically downscale that cluster?
Yes. Yeah, I think, if we look at the way that Web 2 scaled to, global scale, if we want to bring blockchain applications, or really it's applications that use blockchain, if we want to bring that to scale, I think that we need some sort of way to, scale our supply of block space. So auto-scaling is one way to think about this, where you could imagine just as your usage goes up, your fees, because the idea is to smooth your base fee across many chains. So if your base fee hits a certain point, then you could imagine having the infrastructure in place to just spin up another chain and then just start load balancing the execution to that other chain.
I think can probably be done within one chain as well. If you have basically multi-threading within one chain, right? Like dynamically within a chain instead of doing it at the abstract level of let's do multiple chains to scale.
Yeah, I think a lot of people are working on some sort of multi-threading or like concurrency within the EVM. This is a slightly different abstraction, but it's definitely possible to integrate all of that work into our tech stack once it is like battle tested and we know like what the worst case analyses are.
Thanks.
Yes, I was wondering, it's kind of like two questions in a way. So one is, so because of the dependency set, there's basically going to be a click of connected rollups, right? And so I was wondering how coordination is going to happen between them in order to kick out one or add another one because of the dependencies that derive in terms of safety. And also you mentioned how you want to use CK proofs to eventually remove the dependency set, but CK proofs don't give you equivocation prevention. So I was wondering how that unfolds.
Totally, yeah. So basically, it's a governance problem. It's really, how do you guarantee that someone did not add a backdoor to their system? that's really the problem statement, because when you're interoping with a chain, if you're designing a system where you're interoping with chains that may have introduced a backdoor into their system, then that will add a lot of complexity for the application developer. And the application developer needs to now defend against potentially malicious messages. So we've opted for a design where we want to guarantee to the application developer that they won't receive a malicious message like that, and they don't need to like worry about validating the individual messages based on what chain they came from. So that requires some level of governance. In the short term, with the dependency set, the plan is to have guidelines that are open that basically are the requirements. It'll be like being a stage 1 plus rollup, having some amount of economic activity, having an uptime SLA, some amount of usage, and it will allow, the optimism governance system to kind of, ratify adding new chains to the dependency set. It's free for anyone to spin up their own cluster. And then in the longer term, in the ZK world, when we try to remove the dependency set, the idea would be to just it would only work with chains that have a trusted genesis, meaning we know that they did not insert a backdoor into either the code or the smart contracts. And this is just to guarantee that users developing smart contracts don't need to have some sort of allow list with what messages they accept to ensure that all the chains don't have a backdoor, because they share security. And if there's one with a backdoor, then it's kind of the weakest link.
Yeah, but how do you ensure they don't run the same code again with a different state transition and submit that other one? I mean, it's not really a backdoor, right? It's literally just restarting state. You can even do that with TEs.
I mean, so there is like one design with TEs, but like the existence of full nodes like prevent, say, the sequencer from just arbitrarily changing its state transition function. So basically, everyone will reject a sequencer that decides to change the rules.
But a race condition exists where whoever commits first on L1 is the winner one, right? It doesn't matter if everybody rejects it, as long as it's the first state transition that is committed on L1. If it looks valid.
I'm not sure if I understand what you're saying.
We can talk.
Oh, shit. Oh, sorry. We have time for one quick question.
Okay, so as I understand it, the way that this works is that, nodes in the superchain would run a full node for all of the other nodes so that they can verify the logs that are output. Initially, how many chains are going to be in the superchain, and would this potentially prevent a lot of people from running full nodes, because now you have to run a full node for like 40 chains?
Totally. Yeah, that's a great question. So we want to make sure that for home node operators, there's no degradation. So we do want to make APIs publicly available for home node operators to keep the costs down. But that basically means that they're not fully validating themselves, which is not great. We want to make sure people can fully validate as much as possible. For, like economic nodes like exchanges or RPC providers, they will definitely want to run all of the nodes to make sure that they're fully validating, so like they don't get like double spent or they're serving the wrong information. And you are right, this is a scalability bottleneck. We believe it's important to ship iteratively, get something to market, scale to a few chains. Realistically, this will probably break down at not that high of a number. I don't know exactly what that number is. We're going to shoot for something really small. We're going to, just start with a few, maybe see if we can get to 8, and then start really re-architecting in going deep into ZK to see how to if we can get like real scalability improvements from that.
All right. So I have one more question for you. So I'll ask as our next speaker, Shay, is just getting set up. So first of all, you mentioned shared security. Wondering if you can just elaborate a bit more on that. A second part of the question is kind of harkening back to some of the questions over here about, what if a sequencer changes its SDF or something? I mean, is my understanding correct that you are doing, going back to Ellie's talk, something on the settlement layer that ensures that whatever gets when the rollups that are communicating actually settle, that the messages that one rollup sent are consistent with the messages that another rollup received?
Yeah, totally. So your first question about what is shared security?
Yeah.
I think there's two aspects. There's liveness and then there's safety. So the safety part is relevant to the bridge. We want to always guarantee that the bridge is collateralized across all of the chains. So what does this mean? There's a single proof that is required to authorize a withdrawal from the L2. So instead of having a proof per chain, there's one, super proof, you might want to call it, that is able to validate the execution of the L2s altogether in one big chunk.
Yeah, actually, would you say that's sort of equivalent to the way that LD presented it in terms of having some kind of shared settlement consistency check, where you can think of that as, instead of each rollup being able to settle on its own, there needs to be some kind of unified check. And that could be implemented in many different ways, like maybe you're implementing it differently than and some other team might implement it, but that is what you mean by like one single proof. That would be you can sort of, you're talking about it from the perspective of withdrawals, but you can think about it more generally in terms of just when the L1 actually accepts a state from any of these different rollups, which is a prerequisite for withdrawing.
Totally, you're right. Because in the proof itself, and we're designing the proof to be generic to be able to run in both a fault-proof VM and a ZK VM. So like when the proof runs, it will do all those consistency checks before it, finalizes.
Right. So is it fair to say that also, I also didn't quite understand the question that was asked earlier, but I think that answers that question. It seems like if you have some kind of shared settlement proof, then the worst thing that you can do is confuse rollup operators pre-settlement. But once settlement happens, there's no inconsistency of what messages were sent from one chain and what were received by another.
Totally. And one thing to remember, because it is an optimistic rollup right now, we kind of have this difference between the inputs finalizing and the outputs finalizing. So the inputs finalizing is when the data is published to the data availability layer. And because the state transition function is deterministic, you're guaranteed to always get the same end state as soon as the data is published. So that's different than the finalization of the outputs, that's the bridge's view of the L2 state. So that's either finalized with a ZKP or with an optimistic proof.
All right. I think Shay is still just getting a little set up. So maybe one more question here. So what would you say is the worst thing that could happen if before this shared settlement happens, a sequencer passes a message to another sequencer in this interoperability cluster that's just wrong? What are the consequences of that?
Oh, great question. So it is possible to have cascading reorgs. So within a cluster, any chain has the right to choose the security level, the finality level of the messages that they accept. So if a sequencer accepts unsafe messages or like messages with pre-confirmation levels of security, and then when that data is posted back to L1, if there's an equivocation on that pre-confirmation, then there will be a reorg. So this means that because the fork choice rule enforces the integrity of these cross-chain messages, you can have a cascading reorg across many chains.